In this sequence of videos, we're going to discuss the inverse trigonometric functions. The general idea here is, now that we've discussed the trigonometric functions, sine of t, cosine t, and tan t, we're going to discuss their inverses. Let's briefly recall what an inverse function does. So, by definition, the inverse function switches x and y values, or maybe more appropriately in this case, inputs and outputs. So if you have that f of t is equal to y, then that means that for the inverse function, t will be f inverse of y. Let's also take a moment to remember that the inverse function is not the same thing as 1 divided by the original function. Now, the first difficulty that we're going to have with inverse trigonometric functions is that, well, let's recall first that in order to define the inverse function, f of t has to be 1 to 1. That is, f of t has an inverse if and only if it's 1 to 1. And you can tell a function is 1 to 1 in a variety of different ways. Perhaps the easiest way is to look at the graph of the function. When we look at the graph, we can apply the horizontal line test, and if it passes the horizontal line test, then we have a 1-to-1 function. Unfortunately, the graphs for all three of these functions, cosine t, sine t, and tan t, they all fail the horizontal line test. For example, the graph of sine of t, remember, looks something like this. Of course, I haven't drawn any axes, but the graph definitely fails the horizontal line test. And similarly for tangent of t and cosine of t. Now, we've had instances of this before where we had a function which is not 1 to 1, and we wanted to find the inverse of it. For example, let's consider this. Let's find f inverse of 4 for f of t equals t squared. This problem is actually what we would say not well posed, in the sense that since f of t is not 1 to 1, we can tell it's not 1 to 1 because we know this has the classic parabola shape. So since f of t is not 1 to 1, it's not going to have an inverse. But what we can do is we can restrict the domain of t squared. Let's go ahead and restrict t to be between minus infinity and 0. And so f of t would then have domain with domain minus infinity comma 0. We need a 0 there. And graphically what that means is we are erasing the right half of this graph here. So we have made a domain restriction which allows us to have a 1-to-1 function, and now we can begin talking about the inverse. So if I wanted to know what f inverse of 4 is, I can give it a label, and I'm going to give it a label which is t, because the output for the inverse function, remember, is like an input for the function itself, the original function. So I give f inverse of 4 a label, t, and then I write what this means in terms of the original function. Remember, inverses switch inputs and outputs, so this means that 4 would be f of t. But not just that. We also need the fact that these t's, these inputs that are allowed, are the t's that are between minus infinity and 0. So I'm going to write that. So minus infinity less than t less than or equal to 0. Of course, now if 4 is f of t, we know what f of t is. That's t squared, so 4 equals t squared. And the solutions to this are t equals plus 2 or minus 2. So t, which is what we want, right? Because t is itself f inverse of 4, that's what I want to know. It's plus or minus 2, however, I need my t to be between minus infinity and 0, and so I'm going to pick this negative, and we end up with a final answer here of f inverse of 4 equals negative 2. This idea is exactly what we're going to do when we discuss the inverse trigonometric functions. We're going to have a function here that we want to know the inverse of, sine t, cosine t, or tan t, but it's not going to be one-to-one. So we're going to then make a domain restriction. The domain restriction will be something that you just have to know. Then, when we go later on to talk about how to find inverses, we will need that domain restriction in order to do whatever it is that we're trying to do. Find inverses of particular values. You'll see other things as well along the way.